Hello and welcome to the Ryland Report. I'm James Ryland.
And I'm Claire Ryland.
We are so glad you could join us. This is the show where we take just a mountain of historical archives, scientific papers, eyewitness accounts.
Yeah, we sift through all of it. We do the digging so you can get right to the story.
And for today's deep dive, we're going back, way back to the early 20th century.
To a place so remote that, honestly, even with today's technology, it's still incredibly difficult to get to.
Okay, so I want you to picture a map of Russia. You go east, way past the Urals, deep into the emptiness of Siberia.
Right.
Now zoom in on the Tunguska River. The date is June 30th, 1908. It's early morning, maybe 7:00 a.m.
It's quiet, peaceful even.
Until 7:10 a.m.
Hmm.
At that exact moment, the sky didn't just brighten.
It tore apart.
Yeah. Witnesses described a light so intense it actually made the sun look dim. A bluish-white fireball screaming across the sky.
With this pillar of fire, they called it, connecting the clouds to the ground.
And then came the shock wave. And this wasn't just a sound,
No, this was a physical force. A wall of air that knocked people clean off their feet hundreds of kilometers away.
It's like standing in London and getting knocked over by an explosion happening in Paris.
Yeah.
That is the kind of scale we're talking about here.
This is the Tunguska event. It is by far the largest impact event on Earth in all of recorded history.
And the mystery isn't just that it happened. The mystery, the real puzzle, is that for over 100 years, we couldn't find the bullet.
Right. We had the wound, this huge destroyed forest, but no impactor, no crater.
And to really get why that's such a big deal, we have to talk about the sheer energy involved.
Scientists looked at all the data, the seismic readings, the forest damage, and they came up with a number, anywhere between 3 and 50 megatons of TNT.
Let's just pause on that number for a second. Megaton. It sounds so clinical.
It does.
But 50 megatons is essentially the Tsar Bomba, the largest nuclear weapon ever detonated. It's like 3,000 Hiroshima bombs all going off at the exact same instant.
It's world-ending power. And the landscape showed it. We're talking about 2,150 square kilometers of forest just flattened.
Which is an area, roughly the size of Tokyo?
Or London, yeah. A major metropolitan area, completely leveled in a flash.
So our mission today is to figure out what happened. We're going to look at the original accounts from the people on the ground who thought their world was ending.
And we'll look at the expeditions that finally made it into that swampy, remote wilderness.
And we're going to try to answer the big question, was it a rock? Was it a comet? Or was it, something else entirely?
And we have to start with the human element, because before any of this was a scientific question, it was just terrifying.
Absolutely. So in 1930, an expedition led by a mineralogist named Leonid Kulik, he went and collected testimonies. And some of these stories are just visceral.
Mm-hmm.
There was a farmer, S. Semenov. He was at the Vannevar trading post, which, looking at a map, is 65 kilometers from ground zero.
Which should be a totally safe distance. You wouldn't even hear a normal explosion from that far away.
Right. Semenov was sitting on his porch facing north. And he told the expedition that suddenly the sky split in two.
Wow.
He described fire appearing high and wide over the forest. But here's the part that really gets me. He didn't just see it, he felt it.
The heat.
Yeah. He said a heat wave hit him so hard, he thought his shirt was on fire.
I mean, just think about the physics of that. The thermal radiation was so intense that 40 miles away, a man felt like his clothes were literally combusting.
He actually tried to tear his shirt off.
Yeah.
And then the sky closed. A shockwave hit, threw him several meters off his porch, and knocked him out cold.
And when he came to, the sound finally arrived.
The cannon fire, as he called it.
That phrase, cannon fire, it just keeps showing up in the reports.
It does.
I was looking at archives from the Siberia newspaper, dated just a couple of days later, July 2nd, 1908, and they had reports from villagers who saw a pipe or a cylinder shape falling, which then turned into this billow of black smoke.
And they all described artillery.
Exactly. I mean, in 1908, what was the loudest thing you'd ever heard? It was probably artillery. They just didn't have the vocabulary for something like this.
There's another account from the indigenous perspective, right?
Yes. The Shanyagar tribe, they were much closer. A man named Chuchen was sleeping in his hut.
And he was woken up by the birds.
That's right. Not the explosion itself, but by the wind and the sound of birds just panicking. Nature knew something was wrong before the people did.
And then the shockwave hit.
He said it felt like they were shoved into the fire. Again, that sensation of intense heat.
So they crawl out of their collapsed hut.
And they see trees falling down with their branches literally on fire. Chuchen described a second sun shining in the sky. And the thunderclaps just kept coming, one after another.
So while people in Siberia were living through an apocalypse, the rest of the world was just noticing something strange.
Right. They didn't hear the boom, but they absolutely felt the ripples. The entire atmosphere was ringing like a bell.
So seismic stations all across Eurasia registered the tremors.
But the airwaves went even further. They were picked up in Washington, D.C., in the UK, all the way to Batavia, which is modern-day Jakarta. Barometers in London were just twitching.
And then came the bright nights. This is where the story gets really bizarre.
It really does. For days afterwards, the night skies over Europe and Asia just didn't get dark.
We're talking about reports from Sweden and Scotland, where people were taking photographs at midnight with no flash.
They could read a newspaper outside at 1 in the morning.
Yeah, so we have a pretty good scientific explanation for this now, don't we?
We do. There was a study in Geophysical Research Letters that drew a really cool parallel. It's all about high-altitude ice particles.
Yep.
The explosion was so huge, it shot tons of water vapor and dust way, way up into the upper atmosphere. These formed what are called noctilucent clouds.
Which are so high up they catch the sunlight from over the horizon.
Exactly. Even when the sun has set for you on the ground, it's still illuminating these ice crystals 50 miles up. We see a similar thing on a much smaller scale after space shuttle launches.
So you have this global event. You have terrified eyewitnesses. You'd think scientists would be racing to Siberia.
You would think. But, history got in the way.
1908, Russia
Yeah.
was not a stable place. You had
Yeah.
political unrest. And World War I, the Revolution, the Civil War.
And that part of Siberia is already a nightmare to get through. Swamps, mosquitoes, add a war to that, and it's basically impossible.
So you get this huge gap, 19 years of silence.
It wasn't until 1927 that Leonid Kulik finally led an expedition to the site.
And Kulik is a man on a mission. He works for the Soviet Academy of Sciences, and he is 100% convinced that a giant iron meteorite hit the Earth.
He's going there expecting to find a massive crater. He wants to mine the iron for the Soviet Union.
They trek through all this mud and snow. It's a brutal journey. They finally get to what they think is ground zero. They're looking for this giant hole.
And they find swamp.
It's just swamp.
Just swamp, no crater, no hole, not a single piece of meteorite iron. Nothing.
That must have been just crushing for him. But he did find something very strange about the trees.
He did. He found what we now call the butterfly pattern. Right at the center, in an 8-kilometer zone, the trees were scorched, but they were standing upright.
Stripped of all their branches, like telephone poles.
Exactly, like burnt telegraph poles. But surrounding the center, for miles in every direction, the trees were knocked flat, all pointing away from the middle.
Which seems totally counterintuitive. You'd think the trees right underneath the explosion would be the most destroyed.
It's all about the physics of the blast wave. At the very center, it's called the hypocenter, the blast is moving vertically. It's pushing straight down.
So it shears off the branches, but it pins the trunk to the ground.
Right. But as you move away from the center, the blast wave becomes horizontal, and that's what knocks the trees over.
So the standing trees were the proof they were at ground zero. But the lack of a crater, that meant scientists had to completely rethink what an impact even is.
Which leads us to the airburst theory.
Okay, let's break this down, because I think asteroid and I picture a rock hitting the ground. How does a rock just explode in midair?
It all comes down to something called ram pressure. So imagine you stick your hand out of a car window going 60 miles per hour. You feel the air pushing back.
Right.
Now imagine hitting that air at Mach 80, about 27 kilometers per second.
Mach 80, that's just, I can't even fathom that speed.
At that speed, the air can't get out of the way fast enough. The atmosphere basically becomes a solid wall. The asteroid is being crushed by the sheer pressure of the air piling up in front of it.
So it's not friction, it's compression.
It's extreme compression. The rock's structure fails, it flattens out, which increases the drag, increases the heat, and in a fraction of a second, it detonates.
A collision with the atmosphere, not the ground.
Precisely. Soviet scientists actually proved this in the 60s with these amazing little models. They built tiny forests out of matches and wire.
And they blew them up.
They detonated small charges above them, and they perfectly replicated the butterfly pattern. Standing matches in the middle, fallen matches on the outside. It proved the blast had to have come from above.
Okay, so we know how it happened, an airburst. But the question that's been debated for decades is, what was it?
The great comet versus asteroid debate.
For a long time, the comet theory was the frontrunner, proposed by F.J.W. Whipple back in 1930.
And the logic makes sense. A comet is basically a big, dirty snowball, ice and dust.
So it hits the atmosphere and just vaporizes completely. No rock, no crater.
And it explains the bright nights perfectly.
Yeah.
All that water vapor and dust thrown into the upper atmosphere. There's even a possible link to the Beta Taurids meteor shower.
It's a very neat
A
explanation.
little too neat, maybe. In 1983, an astronomer named Zdeněk Sikanina published a paper that really poked holes in it.
What was his argument?
He said a comet is just too fragile. A snowball hitting the air at Mach 80 would have disintegrated way too high up, maybe 50 kilometers. It wouldn't have made it down to 5 or 10 kilometers to do that kind of damage.
You'd need something tougher to penetrate that deep.
You'd need stone. An asteroid.
But then we're back to the original problem.
Right.
If it was a stone, where is the stone?
Well, it's there. You just have to look at the microscopic level.
Ah.
In the 50s and 60s, expeditions started sifting through the soil, and they found these tiny, tiny spheres of silicate and magnetite. And when they analyzed them, they found high ratios of nickel to iron.
The fingerprint of something extraterrestrial.
Exactly. And more recently, a team from the University of Bologna went even further. They looked at the tree resin, the amber from trees that survived the blast.
And trapped inside that resin from 1908.
They found particles with a composition that matched rocky asteroids, not comets.
For me, though, the thing that really cemented the asteroid theory wasn't from 1908 at all.
Chelyabinsk, February 15, 2013.
That was a real wake-up call.
It was. The Chelyabinsk meteor was a stony asteroid. Smaller than Tunguska, for sure, about 20 meters across, but it did exactly what the theory predicted. It exploded in an airburst.
And this time we had dash cams, we had sensors, we had data.
So much data. And when scientists took the Chelyabinsk data and scaled it up, it was a perfect match for the damage patterns at Tunguska. It proved a stony body can do this.
So the consensus now is pretty firm. Stony asteroid. But there's always a loose end or two.
And we have to talk about Lake Cheko.
This is a fascinating detour. Lake Cheko is this small bowl-shaped lake about 8 kilometers from the epicenter.
And in 2007, that same Italian team from the University of Bologna, they proposed that Lake Cheko is the impact crater.
The idea being that one fragment of the asteroid survived and actually hit the ground.
The initial evidence looked pretty good. The lake bed is conical, which is unusual, and they had magnetic readings that suggested a big, dense rock buried under the mud.
It's the perfect answer. The crater was there all along, just filled with water.
But then, in 2017, Russian scientists went back to double-check. And this is where it gets really clever.
Okay.
They drilled core samples from the lake bed, and they were looking for a very specific isotope. Cesium-137.
Which comes from?
Mid-20th century nuclear bomb tests. It's a perfect timestamp. It doesn't exist in nature before the 1950s.
So they used it to date the layers of mud.
Exactly. And they found the cesium layer near the top, right where it should be. But then they kept drilling, and the layers of sediment underneath were perfectly calm, perfectly stratified.
Not the chaotic mess you'd expect from a violent impact.
Not at all. They found layers that were at least 280 years old. That lake has been sitting there quietly since long before 1908.
So Lake Cheko is just a lake.
Just a lake that happened to be in the wrong place at the wrong time.
All right, so let's zoom out. We have a stony asteroid about 60 meters wide. It explodes with the force of thousands of nukes. It flattens a forest the size of a city. Why does this matter to us right now?
It matters because of frequency. For a long time, we thought an event like Tunguska was, a once in a few thousand years kind of thing.
But our data is getting a lot better.
It is. Based on NASA satellite data, newer estimates suggest a Tunguska-sized event might happen once every millennium, which still sounds rare.
But smaller events, like Chelyabinsk, happen much more often. And the Torino scale, which measures these hazards, rates a Tunguska object as an 8.
An 8 is localized destruction. And localized is a very polite word for what would happen if that airburst didn't happen over a remote Siberian forest.
If it happened over New York or London.
It would be a catastrophe we can't even comprehend. Total devastation. That's why understanding Tunguska is so vital. It's not just history, it's planetary defense.
This is a sobering thought. We're living in a cosmic shooting gallery, and we're only just now learning how to track the bullets.
We are.
I want to leave you with one final image to think about. At the blast site, there's a big boulder. It's known as John's Stone. And for years, people hoped this was it. This was the piece.
The smoking gun.
But analysis shows it's just quartzite, a terrestrial rock.
A rock from Earth?
Yeah. But it just sits there. In the middle of this place, it was completely turned upside down by something from the stars. And it's a reminder that in a landscape hit with that much force, telling the difference between what belongs to Earth and what came from the sky, well, That's a story that might never be fully closed.
It really makes you look up at the night sky a little differently, doesn't it?
It certainly does. Thank you for listening to this deep dive on the Ryland Report.
Thanks for joining us.
Goodbye.
Goodbye.